What's going on, you guys? Welcome back to another Tutor Toby video. So in today's video, we'll be going over another special set of equations called Bernoulli equations. So these, just like what we have been doing, are first order linear differential equations. And they're in the form dy over dt plus q of t, so just some random function of t, which is what y is derived with respect to, times y is equal to p of t times y to the a, where a is just some element to r. So a is just some number, 1, 2, 3, 1.5, something like that. Okay, so we first notice that this isn't quite in terms of our integrating factor method. So it's not quite our integrating factor method. So just from last time, as a quick reminder, I'll write it down again. So duplicate, and our integrating factor method is just this equation, but without that. So this integrating factor method needs to be in this form, right? Okay. So how do we get this into our integrating factor method form that we know we can solve, right? Well, let's just take a guess. So right away, let's get rid of this side right here. So I'll just duplicate this again real quick, drag it down, and let's just get rid of this one right here. So in order to get rid of it, we just divide the whole thing by y of a to get y prime all over y to the a plus q of t y to the, so this is going to be 1 minus a, right, if I want to write it all in the exponent, equals p of t. Okay, so now again, we remember that we really want to get it into this form. So how do we want to get it into this form? Well, something that's really common in math is you just take a transform. So you have a relatively hard equation to solve, or like an integral, and you take a transform to turn it into a form that you do know how to solve. So this is like the U substitution in integrals from Calc 2. So for this one, we know that we want to get it into a term of first exponent. So how about we just make a new variable, call it v, and we have that equal 1 minus a, right? That's just because now I can just substitute v in right here. So we get y prime all over y to the a plus q of t times v is equal to p of t. So this is looking a little better, right? But we have two variables now. So this is in terms of two different variables, y and v. So let's figure out what this y prime would be. So y prime is the same as dy over dt. So let's just take a derivative of my y on each side. So let's implicitly derive this from Calc 1, and we get dv is equal to y to the 1 minus a minus 1, which is just going to be minus a, and then we get a multiply by 1 minus a, and then we're deriving with respect to dy, right? So we write a dy right there. So now we can just divide each side by time, or by a dt, and we get this. Okay, cool. So now from this, we can solve y prime, which is dy dt, is equal to y to the a, 1 minus a, v prime. Cool. So now we can actually substitute this right here in terms of this, and we get, let's just draw some arrows so we know where it comes from. So we get y to the a times 1 minus a, v prime all over y to the a plus q of t, v equals some p of t. Okay, so what's really cool about this is we see that these two right here immediately cancel, and we're left with a form 1 minus a, v prime plus q of t, v equals p of t. And this is exactly, or not quite exactly, but really close to, I'm going to say, integrating factor method. IFM. So how do we get into integrating factor method form? Well, all we have to do is divide by my 1 over a. So we get v prime plus q of t, v, all over 1 minus a equals p of t all over 1 minus a. And then we know how to solve this. We know how to solve this because this is just integrating factor method, but with a little bit of a scaling factor right here. So I know that a first derivation can always be a little bit abstract, so let's go into an example. Alright guys, so now for an example of a Bernoulli equation, let's just solve this one. So let's say t squared y prime minus 2t times y is equal to 3 times y to the 4th. Okay, so the first thing we notice is that this isn't quite in the form that we want. So remember that the form that we want is y prime plus some function of t times y is equal to another function of t that doesn't necessarily have to be the same times y to the a. So look, right here, this needs to be 1. So we need to divide this equation by t squared. So that gets us y prime minus 2 over t times y is going to be equal to 3 over t squared times y to the 4th. Okay, so now from this one, we can divide by y over 4. So we get y prime, y4 is minus 2 over t times, let's see, y to the negative 4 plus y to the 1 is going to be equal to y to the negative 3. It's going to be equal to 3 over t squared. Okay, cool. So now this is in the form that we, or at least this was in the form that we actually wanted, and now we have this. So remember that we need to make this into a regular like v to the first, or whatever variable you want to call it to the first. So we let that be our transform. So we say let v equal y to the negative 3rd. Therefore it follows that I'll write it as v prime is equal to negative 3 y to the negative 4th times y prime. Okay, so then from this we solve y prime is equal to negative 1/3 y 4th v prime, and we can substitute these two things back in to this to get negative 1/3 times y to the 4th times v prime all over y to the 4th minus 2 over t, y to the negative 3rd we just called v, and then that's still equal to 3 over t squared. Okay, again, we can see that these two cancel, so we're left with negative 1/3 v prime minus 2 over t times v is equal to 3 over t squared. Cool, so now we're close to our integrating factor method form, but we just have this little coefficient right here. So that's easy to get rid of. We just multiply each side by negative 3. So we get v prime plus 6 over t times v is equal to 9 over t squared. Okay, so now for our integrating factor method, we use this function of t right here. So we say u is equal to e to the integral 6 over t dt, which is equal to e to the 6 ln of t. Okay? And then remember that we don't really have to add a constant here. It's like a special thing. So now what do we do? So I'm a little stuck because this is pretty complicated, and I really want to simplify it down. And I notice that I have a ln in the exponent, but there's this pesky 6 right here. So quickly, I remember my log rules. So this is actually equal to e to the natural log of t to the 6th, right? And now, what do we get? Well, we get a nice cancellation of those two. So this is just equal to t to the 6th. So that equals u. So now remember, we multiply u on each side. I'm just going to write it like this as a big multiplication. And then we have this special property where this is just equal to u times v. And then this side was multiplied by u, so I'll just write it as 9t squared times t to the 6th. Okay, so now I can cancel this out, and this becomes t to the 4th. And now, get rid of that too. And now to get rid of dt, I can just slap on an integral. Okay, so my u, so this is going to be u times v is equal to the integral of this. So what is the integral of this? Oop, and remember right here, I dropped a negative when I multiplied by -3, remember? Okay, so now that I have that, I'll just slap a negative right there. So now I have -9 over 5 t to the 5th, and this time I do have to add a constant because we're doing an indefinite integral. So plus a constant, and now I can substitute back in for u. So this is going to be t to the 6th times v, t to the 5th plus c. So then I get v as a function of time is just equal to, I'm write it like this, and we will see why just a tiny bit later, but you could write it any way you want. So we have this, and now we ask, okay, but I want to solve for y, not v. So what was my y again? Oh, well, look at that. My y is given right here as a function of v. So then I can just plug in y to the -3rd. It's still a function of time, is equal to just this whole thing right here. Okay, so now it's pretty easy to solve for y. So first we'll invert it, because this is technically y over this, right? And we want y cubed. So we'll multiply by -1. So this is going to become t to the positive 6, and then this is going to be the same, except it'll be to the -1st power. And now all we have to do is take a cube root. So those are cube roots, hopefully. So then we get y as a function of time is equal to, well, you can see that this is going to pull out, so that's going to be t squared times, and then this group right here is going to be -1/3. So we can also write this as t squared over cube root of c plus minus 9/5 t5. Cool. So that is our solution. So now, if you want, you can stop the video here. Thanks for watching, and I hope you learned something. Otherwise, we can always do a double check to make sure that this is a solution. So to check if this is a solution, I will copy and paste this so we know what we're trying to verify. So my y prime is going to be equal to, oh, that is ugly. Alright, just kidding. I'm not going to verify the solution. If you want, you can plug it into Wolfram Alpha, check if I got the right answer. Otherwise, just believe me that it is the right answer, and I hope we learned something. Thanks you guys so much for watching, and be sure to stay tuned for our next video.